Okay, welcome to your first set of lecture notes in AP Chemistry. The way we're going to set the class up is you're going to watch the lecture notes as homework, and you're going to do the problems in class. The reason that we're doing that is so that I can guide you on the problems if you need help. Now, sometimes there will be problems which I don't help you because that, for instance, on a quiz, but the homework questions you'll be allowed to ask. You'll be allowed to ask for help on them, and I think that this will make the class a little bit easier in general. So we're going to start with stoichiometry. This is what you really need to get going in AP Chemistry. So atomic masses, carbon, the carbon-12 specifically, that isotope of carbon. Remember what an isotope is. It is an element with differing numbers of neutrons. So any element, so like carbon always has 6 protons. If you get a 7th proton, you're no longer carbon. So that's some review from pre-AP chemistry. However, you can have more or less neutrons. So carbon-12 has 6 protons and 6 neutrons. And we have defined it to have exactly 12 atomic mass units. So its mass is 12 by definition. We've defined it that way. All other elements' masses are defined based off of this one. Okay. The way we figure out something's like an element's mass is with a mass spectrometer. This allows us to really take some compound and figure out what elements make it up based off of the masses we get out. So the way this works, there's kind of a description down here, but I'll try to sum it up in my own words. You put a sample in, it could be anything, and this coil right here, let me zoom in for you. This coil right here heats up the sample to the point that it breaks all of the intermolecular forces holding the sample together, and then it even breaks the chemical bonds. So that's how hot we're getting this thing. We're really just breaking this thing into particles, okay? We then push these particles through and they get hit by an electron beam. The electron beam knocks off other electrons on these particles, making them positively charged. These positive ions are pushed through these two slits to accelerate them using an electric field. So you can imagine if there's like a negative side here and a positive side here, once they get pushed through here, they're going to accelerate that way. The accelerated ion beam then passes through a magnetic field. This is a little beyond, well, I shouldn't say it's beyond the scope of this class, but it's something you probably haven't learned. If you're moving something that has a charge, so I move these positive ions, they're actually generating a magnetic field, okay? So anything that's moving that has charge is generating a magnetic field. These things are moving, they generate a magnetic field, and that interacts with this magnetic field right here. Okay, this causes these to deflect. All right, and you might say, what the heck does this have to do with mass? We got very, very complex very quickly. Well, really, the way these things work is based off of the mass. These things are going to deflect at different by differing amounts. The more massive something is, the less it's going to deflect. That should make sense a little bit if you think about it. Things that are more massive do not get moved around as easily as things that are less massive. So if everything's getting pulled up in this particular case, right, the more massive things are not going to get pulled up as hard. So the more massive things will be on this side of the plate. The less massive things will be up here on this side of the plate. Okay, hopefully you can see this cursor. I know it's hard to see it moving around, but the things that are pulled up less are more massive, right? They don't get pulled as hard as the things that are less massive. And this is how we analyze the different elements in something. So the way we can do that is just we know the given masses of the elements, and if you put something in here based off the deflection patterns you get, you can tell what elements you're dealing with. Okay. And you can see here how they define how we got like carbon 13's mass was based off of like a deflection ratio. That's how you get this 13.003355 AMU. It's based off of the ratio of deflection. Probably not going to do that in this class. All right, average atomic masses. So these are what you're really looking at when you see an atomic mass on the periodic table. So let's go to ptable.com real quick. So when you see one of these numbers, like carbon 12, so you can see the elements pictured over here. Carbon has an atomic mass of 12.011. When I say that carbon has an atomic mass, I don't mean carbon 12 has that atomic mass. I mean carbon's average atomic mass is 12.011. The reason is that there are differing isotopes of carbon. Okay, you could have carbon 12, carbon 13, carbon 14. Most of the time, we have carbon 12. Carbon 12 is the most common isotope. You're going to have some carbon 13 and carbon 14. Those small amounts are what accounts for the average mass being slightly higher than 12. Okay, percent abundance, this is really just to figure out how much of a given isotope you have. So you would take the number of atoms of an isotope, right? If I want to know what percentage of carbon is carbon 13, I would take the number of atoms of carbon 13 divided by the total number of all the carbon atoms in that sample. That would give you a decimal, and you would just multiply it by 100%. So that would give you what percentage you were dealing with. All right, counting by mass. We're going to do that a lot in this class. So this is how we measure things in chemistry. And really, in your day-to-day life, you do this too. So like, if you're going to buy, say, the example they use here is peanuts. But if you're going to buy like, what's something that you weigh out at the store? So a lot of times you'll see that like fruits are sold to you by weight, right? Like bananas. The reason that is you don't want to, let's say someone comes through with a cart full of bananas for whatever reason. I don't know why someone would do that. Maybe there's a gigantic party going on making banana splits. I don't know. Okay, someone comes through with a cart full of bananas. Rather than pulling every one of these banana bushels out or bundles of bananas out and counting each banana, a quicker way is to just put it on the scale, right? And weigh out these bananas and then charge them by the average mass of the bananas, okay? Same thing with sugar. I think sugar is a better example, right? The only way we're selling that by weight, right? We're not counting out how much sugar crystals are there. All right, mass spectrometer to determine isotopic composition. So let's say we want to know what isotopes are in a sample. You load it into this thing up here. Okay, and this is what the data is going to look like for a mass spectrometer. You're going to get something like this over here on the left, ion beam intensity at detector. All that means is that the more ions you have at the detector, the higher these peaks are going to be. So if I'm getting mostly, say, neon 20 here, this is going to be much more, you're going to have a much higher peak here. Whereas neon 22 is lower and neon 21 is the lowest. What that means is that most of the sample is neon 20, then 22, then 21. So if you go back up here, neon 20 would be the one that deflected the most, right? Because it's the least massive. Neon 22 would deflect the least, and neon 21 would be in the middle. These intensities would look, let me see if I can draw it. Get the pen tool out. So if we were to draw our own lines here, neon 20 would be the most intense, right? Let's see if this tool works, if it detects different pressure sensitives. Neon 21 would be less intense. And neon 22 would be a little bit more intense than 21. I know it's hard for me to for you to see that, but see how this one's the most intense, least intense, and then in between the two. That's how this data is that's how it's collected, is based off of ion intensity. So this data down here is an interpretation of that. All right? If my little pen app will come back up, I'll erase it. Okay. Here is the same data with numbers put to it. So you can see 91% of the ion beam intensity was neon 20. So all that translates to is 91% of the sample is neon 20, 9% is 22, 0.3% is 21. Okay, so how do you use that to figure out average mass of an element? Well, it's pretty straightforward. It's just some multiplication and addition. So when a sample of natural copper is vaporized and injected into a mass spectrometer, the results shown in the figure are obtained. Use these data to calculate the average mass of natural copper. The mass values for copper 63 and copper 65 are 62.93 and 64.93 AMU respectively. Okay, so you might pause the video now and try to think about how we would start this problem off. We want to figure out the average mass of copper. So you might pause it and just do some thinking on your own. Okay, hopefully you did that. If not, in the future when I suggest that you pause the video, try pausing it and thinking about it. But if you're in a hurry, I understand. So let me zoom in on this a little bit more for us so we have some room to work. We want to know the average mass of copper. So we've got copper 63 has a mass of 62.93 AMU. Okay, and what's the percent of copper 63? Well, if you look over here, it's 69.09. So we'll multiply by 0.6909, right? That would be the mass contributed by copper 63. Let's do copper 65 now. It has a mass of 64.93. So 64.93 times, and we've got a percent abundance over there of 30.91. So times 0.3091, right? We're going to multiply these two together and get some number for each, right? We'll then add those two together, and what we get will be the average atomic mass for copper. Okay, if you multiply these two, so multiply that times that times that, add those two results together, that's the average atomic mass for copper, right? That's the mass contributed by copper 63 and the mass contributed by copper 65. Together you get the average mass. So let's go ahead and work through that on the calculator. I'm going to do it on my phone. That's what I would suggest you do, unless you have a fancy calculator. Then do it on that. So 62.93 times 0.6909. That one is 43.48. Okay. Over here, 64.93 times 0.3091. Add these together, we get 20.06. All right, add these. So plus 43.48. 63, that's a terrible 6, but we're going to have to live with it. 0.55. That's your answer. See if I can box it. Okay. Well, I'm still learning the pen tablet thing, so it's not my best box, but that's okay. So down here on the notes, the answer will usually be displayed. Most of the time it's right, but I can't guarantee you that this will always be the right answer. If you work through the problem a couple times and you're getting a different answer than either me on the video or what's listed down here, and you can't figure out why you're getting a different answer, come talk to me and we'll work through it. There's a chance that I did it wrong, right? Okay, we'll end the video there. I'm limited to 15 minutes on each of these videos, so there'll be more videos for you to watch. In general, expect about 45 minutes worth of video per night to watch. Okay.